Thank you and welcome to my talk. My name is Florian Altermatt, and I want to start with saying that it is a true privilege to have been part of the DNA Connect cost action over the last years, culminating in this wonderful conference over the last few days. I will be speaking about the challenges and opportunities for implementation of eDNA biomonitoring in riverine systems. And I will specifically build on our experiences we made when interacting extensively with stakeholders in Switzerland and developing implementable guidelines. As you all know, freshwater ecosystems are globally under very high pressures, with global change and massive biodiversity loss affecting ecosystem functions and ecosystem services provided by these freshwater systems. Obviously, we must reverse these trends. And to do so, we must implement adequate conservation and management policies. But we also need monitoring tools to describe the state and change of freshwater ecosystems to adequately inform policy making. Bluntly speaking, we need simple numbers telling us about the state of aquatic ecosystems and the direction these systems take. Without such numbers and indices, it is very difficult to change management and policies. Until recently, however, most biomonitoring in riverine ecosystems and the numbers thereof were coarse at best. For example, in many countries, biodiversity in individual rivers is often only monitored once every few years. Thinking of typical organisms such as aquatic insects with generation times of a few weeks or months, this would be analog to a forest inventory where the last data point was collected somewhere in the 16th century. You see that this is inadequate and it clearly can and should be doing better. Our colleagues from aquatic chemistry show that it is actually doable. For example, they have implemented in many riverine systems semi-automated sampling stations which can screen hundreds of chemicals in real time with a resolution of hours to days. This is what we want for bioassessment as well. Such highly integrated and spatially resolved data on water chemistry have then actually also changed our policies and implementation substantially. Importantly, and key to the success was that these measurements must be taken in a standardized and replicable manner. As you know, the use of environmental DNA, that is DNA retrieved from an environmental sample, has been postulated as a way to achieve this and to revolutionize biomonitoring and bioassessment. In the last few years, we have been saying that it can be used to get a better monitoring of individual species, whole biodiversity surveys, or for establishing biotic indices. And as you have learned the last days, progress has been huge, and we have not been shy of making promises to its potential. Thus, we are witnessing, or we are even part of a revolution in biodiversity sciences. However, as with all of revolutions, these transition times are not always very simple. They come with possible turmoil. Old rules and habits are given up. New rules and constitutions are written, and new policies are implemented. Rapid initial success, broad applicability, and advances in sequencing technologies have raised very high expectations about the potential of environmental DNA biomonitoring. Now, as with all of these revolutions, true success requires a formal implementation and establishment of new routines. And I'm asking you, who is guiding us in these times? In this talk, I will address three aspects where I see challenges and need for guidance for a successful implementation of eDNA biomonitoring. These are different targets, different inference, and different guidelines. I will now address each one of those and will specifically discuss my understandings or different expectations I experienced when having interacted with stakeholders on this topic over the last years. The first point is with respect to the organismal groups targeted. In traditional approaches, these are, for example, invertebrates or fish or diatoms. And there is well-established methods on how to adequately sample them, such as kick netting or electrofishing. One of the biggest problems, however, I think for a successful implementation of DNA biomonitoring is that we are often trying to make a like-for-like substitution of these methods. Because we are trying to optimize eDNA biomonitoring for exactly these very same taxonomic groups. While this may look promising at first, I think it comes with two major problems that are not only hindering implementation, but I think could actually also kill the revolution. Firstly, we forget that these groups had been chosen for the use in traditional methods because some of other constraints. For example, that was the ability to sample and identify these target organisms. And so they were chosen to be not too small or belong to groups where sufficient number of experts were available for their identification. It would be now a pity if we drag on some of these constraints to eDNA-based approaches by maintaining such a focus. In the worst case, we are not only trying to mimic a limited approach, but we'll even fail because our new approaches are fundamentally not able to match these approaches adequately. This is, for example, the case when traditional groups are monitored that are highly polyphyletic. For example, the macroinvertebrates looked at consider and contain mollusks, polychaetes, crustaceans, some insect orders, but also cnidarians and poriferous. Commonly, these groups are not even resolved to the same taxonomic level, or the resolution differs for different lineages. While I think this is fine for the classic monitoring, because it was based on the size and practicability criterion, it simply doesn't work if you try to use an eDNA-based approach. Primers are best designed to be targeting all organisms of monophyletic groups. Thus, having a selective polyphyletic coverage is thus not what we should aim for. Secondly, by keeping the, I would say, limited target, we miss a unique opportunity if we do not expand to other taxonomic groups looked at. Keep in mind that most traditional biomonitoring focuses on a very small part of the phylogenetic tree, for example, invertebrates or vertebrates or diatoms. There is no reason why we should keep doing this. It is actually quite likely that information to describe the state and change of freshwater ecosystems is also contained in other groups. In a way, it is diversifying our portfolio to include more organisms being used for the assessment. I will here just give one example to outline this potential. We took water samples for eDNA analysis up and downstream of wastewater treatment plants across Switzerland. This was done in parallel to classic tick netting of macroinvertebrates. However, instead of counting the bugs, we sequenced the microbes from these environmental samples. Looking at the bacterial communities, we not only find there is a characteristic change in these communities in places where there is a wastewater treatment effluent, making the communities more similar downstream of such inflows, indicated here by the violet compared to the blue circles. But we also find that the communities sampled are indicative for land use practices and land use types found in the surroundings, shown here in these wordles. So we could here link observed communities of bacteria to land use practices, outlining a huge potential for biodiversity monitoring. So concluding to the targets, I think we should not stick to targets that were chosen because of different and now obsolete boundary conditions. I think it's very important to make use of the novel opportunities, including microbes or previously unresolved invertebrate groups. And finally, if we aim for replication or paralleling previous technologies, then I think we should do that at the index level and not at the level of individually taxa measured. Now let's move on to the second challenge where I think some guidance is needed, that is with respect to different inference. Traditional biomonitoring in riverine systems is based on a local scale perspective. Literally, you turn a stone in a river to see what lives there. eDNA-based approaches, however, have a very different, namely a catchment scale inference, because of the passive transport of the eDNA signal flowing in water. It is as simple as that. DNA in a river is washed downstream. However, this affects comparability with traditional methods, but it also creates novel opportunities. I again want to highlight this with an example. We studied about 60 sites in a large catchment in Switzerland, covering small to medium-sized and larger streams. We sampled and sequenced the DNA and compared it with classic sampling on macroinvertebrates. And we observed something that I think is quite commonly seen. Namely, at the catchment scale, that is at the level of gamma diversity over all of this catchment, we have a pretty good overlap and match with the KickNet data. We find about the same number of taxa and have a good and large overlap with the identity of these taxa observed by both methods, here indicated by the violet and green circles. In this case, we even had fortunate long-term data where we could put that in a historic context. However, comparing not gamma diversity, but looking at individual sites and looking at alpha diversity, things look much less good. We not only have much higher variation between these two approaches in local richness, here given for KickNet and eDNA data, but we also find that the taxa found in individual sites are often not satisfyingly matching. And this has been, in my experience, one of the most challenging aspects when talking to managers and stakeholders, partly also because of the overly optimistic expectations we as a community may have created. Here, for an adequate implementation, we need to be talking straight. We should tell stakeholders and managers that we look at a different inference. It is the moment of the revolution where you have to not only talk about visions, but also about the new realities. Importantly, however, the fact of passive transportation of DNA in flowing waters gives you also completely new opportunities. We can, for example, use such hydrology-based models, which we developed to predict local DNA concentrations by integrating both transport as well as decay of eDNA in order to exploit this catchment level inference. These models, here are the predictions in the top right map, are parameterized using the local eDNA samples and can then not only give us a space-filling prediction of biodiversity, does a totally new resolution at the scale of few hundred meters of river stretches, but can also, and that I think is very important, give us a better and more accurate description of biodiversity than just looking at the eDNA data themselves in the middle panel, which they are actually based on. And we validated that this inferences gives a completely unprecedented and accurate level, as indicated by the lower panel in this figure, showing a very high accuracy. For implementation, however, this means that you have to change our objectives with past sampling strategies. And we may make use of these novel opportunities by adapting our sampling. It, for example, means that the sampling strategies for eDNA biomonitoring in riverine systems will depend on the expected distribution of the species targeted. For example, species that are uniformly or point-like distributed. And thus you can't take just a one-to-one sampling strategy used for, let's say, KickNet or electrofishing. Using a simulation approach, we have evaluated different sampling strategies and came up with simple rules of thumbs for best practices of sampling site selection for eDNA-based sampling in riverine systems, suggesting that for taxa that are concentrated in hotspots, or when you can only sample a few sites due to logistic or financial reasons, you should sample in the downstream part of a catchment. On the contrary, for taxa that are more evenly distributed, or where many sites can be placed, one should preferentially locate the sampling sites more in the upstream area. Thus you see that for implementation, this means we have to walk all the way through with the revolution, and not only change and adapt the methodology, but also the sampling strategy upon which these methodologies are executed. So now I will come to my last and third point, namely the need for guidelines. With all of these novel opportunities and all of these changes, new technological innovations, we need guidelines for all aspects and steps of eDNA-based biomonitoring, from sampling to processing to sequencing and bioinformatics. This is typical for revolutions. They come with new constitutions. And I think it is now the time to focus on this aspect. And it is very important to remember that their writing has very long-lasting effects, and we need to be careful on how to do this. So what makes a good constitution? It needs to be generally supported. It also needs to be generically valid so that we can build on it and have fairness and comparability. Think of constitutions in your own country, and you will see where you can succeed or fail with this. And lastly, these constitutions need to define high-level principles and be flexible to have amendments and changes in the day-to-day lawmaking. We have done this for the Swiss Federal Agency for the Environment, where we have written guidelines on eDNA applications for biomonitoring and bioassessment in aquatic systems. On the one hand, we have described in rather high detail how things can be done, giving hands-on protocols and case examples. We experienced that this was very much wanted because it bridges the gap between the scientific literature with their often short method descriptions and the need of practitioners to see how these things can be done step by step. If you're interested in these guidelines, by the way, they are available in English, German, and French and can be freely downloaded. More importantly, however, than these cookbook instructions only, I think we also delimited best practices and documentations of procedures of eDNA-based approaches. We there proposed common standards that should be valid and allow also long-term comparability in a field where many aspects of the methods are still rapidly changing. This is a key aspect for successful implementation, that you have this long-term comparability. As a scientist, I'm not really interested in repeating something I've already done once. I actually move on and try new things, right? However, long-term comparability and consistency is truly needed for implementation. The guidelines that we proposed here have been therefore developed in close discussion with stakeholders and the environmental agency, and I think they should be long-lasting. For example, we described best practices and high-level rules that can be standardized with respect to sampling, the laboratory process and settings used, as well as the subsequent molecular laboratory work and the data processing and storage. This, for example, includes aspects that may be obvious, such as the need for an adequate and standardized training of people involved. But it also covers less obvious aspects, such as if and how data, extracted DNA or information on primers and bioinformatic pipelines must be documented. I think it is absolutely critical that we get this transition state right to solidify the revolution in biodiversity sciences given by environmental DNA approaches. So what do we do next? What is the way forward to make that happening? I think one aspect is that we should focus on the strengths of the novel approaches and not on their limitations or their matching with past approaches only. It is important that we do not miss novel opportunities. At the same time, it is very important that we acknowledge that it is a different signal detected. We also should highlight that this DNA signal is subject to spatial and temporal decay, which will affect especially the spatial inference. We also should be clear about the precision and accuracy of that signal. We have to agree on common and lasting standards. And if we aim for matching traditional approaches to eDNA-based approaches, I think we should do that at the index level. So now let's wrap up. I started with the premise that we are in the middle of a revolution, and to make it a success, we need to be clear about its goals. Most importantly, and we should be straight and realistic, both with respect to the potential, but also the challenges. Dreaming of a revolution is good, but it only sticks if you implement it and build a formal and legal framework where it is institutionalized. I would say we are halfway in. And to succeed, we should move on forward with realizing these three aspects need to be resolved and clearly done. We should consider all of biodiversity. We should focus on such a space integration, and we should decide on common rules and practices. With this, I would like to thank you very much for your attention, and I'm looking forward to your questions and feedbacks. You can also reach me by email. And obviously, I would also like to thank to all my current and past members and colleagues without whom all of this work would not have been possible. Thank you very much.